Hello students, in the last lecture I was discussing about the memory organization of 8051 microcontroller, and there I started discussing about the program memory of 8051 microcontroller. So we'll continue or we'll move ahead with the same discussion in this lecture also. So I've told you that Intel 8051 has an internal or built-in ROM of 4 kilobytes. That is, it has on-chip ROM of 4 kilobytes, and it can be extended up to 64 kilobytes by using an external program memory. What I'm trying to say is that 8051 microcontroller has on-chip ROM of 4 kilobytes, that is internal, that is on-chip ROM, and it can be extended up to 64 kilobytes by using an external program memory. So in case of 4 kilobytes of internal ROM, the address space is 0000H to 0FFFH, and if the address space, that is the program address, exceed this value, then the CPU will automatically fetch the code from the external memory. So this program allocation, this whole program allocation can be done in two ways depending on the status of EA bar pin, that is external access pin. So it is an active low pin since bar is there, which means it activates when low signal is provided. That is, when it is grounded, it gets activated. So when the external pin, EA pin, is pulled high, that is when it is connected to plus 5 volt VCC, when it is pulled high, the CPU first fetches instruction from the internal program memory, that is of 4 kilobyte. So it first fetches instructions from the internal program memory. It is having the address range 0000H to 0FFFH, and if the memory address exceed the limit, then the instructions are fetched from the external ROM in the address range 1000H to FFFFH. So this is how, this is 4 kilobyte, this is of 60 kilobytes, so this is how it will make 64 kilobytes. So this is one technique of program memory allocation in 8051 microcontroller, that is when external access pin is pulled high, we will have 4 kilobytes of on-chip ROM and 60 kilobytes of external memory, thus making up 64 kilobytes of program memory. Now there is another way to fetch the instructions, that is ignore the internal ROM. This is another way of fetching the instructions, that is ignore the internal ROM and fetch all the instructions only from the external program memory. For this scenario, the EA pin, that is external access pin, must be connected to ground. So when it is connected to ground, it is activated, means external program memory will be accessed now. So when it is connected to ground, it is activated, and in this case the memory address of external ROM will be 0000H to FFFFH. So that is total external program memory of 64 kilobytes, that is over the entire range of 0000H to FFFFH. So this mode is selected when EA bar is connected to the ground. So when EA bar is connected to the ground, we do not have any internal program memory, the internal program memory will be ignored, and the external, there will be only 64 kilobytes of external memory having this address range making up 64 kilobyte, and all the program or all the instructions will be fetched from the external memory. And if EA pin is connected to plus 5 volt VCC, that is pulled high, then we have 4 kilobytes of internal memory and 60 kilobytes of external memory will be used, thus making up total of 64 kilobytes. So this is how 64 kilobytes of program memory allocation can be done in two ways depending on the status of EA bar, that is external access pin. Now moving ahead to the data memory of 8051 microcontroller. So the data memory or RAM, we can say RAM, that is random access memory, as I've told you. So the data memory or RAM of 8051 microcontroller stores temporary data and intermediate results that are generated and used during the normal operation of microcontroller. So original Intel's 8051 microcontroller has 128 bytes of on-chip RAM that I've discussed also when I was discussing the features of 8051 microcontroller, that it has on-chip RAM of 128 bytes. But almost all modern variants of 8051 microcontroller like 8052 microcontroller have 256 bytes of on-chip RAM. You can see this in the features also. 8051 has on-chip RAM of 128 bytes, whereas 8052 has on-chip RAM of 256 bytes. So here we'll discuss only the original 8051 microcontroller, that is having the on-chip RAM or on-chip data memory of 128 bytes. Now this 128 bytes of RAM, that is from 00H to 7FH, that is making up 128 bytes. So this 128 bytes of RAM are addressed by either direct or indirect addressing, and these 128 bytes of RAM is divided into three parts. So what are the parts? The first is registered banks. This is the register bank part, having the bank 0, 1, 2, 3 from 00H to 1FH, and it is of 32 bytes. So what I am trying to say is that since the 8051 microcontroller has on chip RAM of 128 bytes, so this 128 bytes is divided into three parts. So in 128 bytes, the first 32 bytes is taken by the register banks. So register banks means it will have bank 0, 1, 2, 3 and the address is 00H to 1FH, thus making the 32 bytes. So first 32 bytes is occupied by the registered banks. Now next 16 bytes is occupied by the bit addressable memory. Bit addressable memory, that is having the address range 20H to 2FH. So this is making the 16 bytes. Next 16 bytes of 128 bytes of RAM. And the last 80 bytes of 128 bytes of RAM is occupied by general purpose register, or you can say scratch pad area, and it is having the address range from 30H to 7FH. So this is making up the 80 bytes. So again I am repeating the first 32 bytes, that is from memory address 00H to 1FH, consist of the registered banks, and it consists of 32 working registers that are organized as 4 banks: bank 0, bank 1, bank 2, bank 3. I'll discuss about this thing in detail. Then the next 16 bytes is occupied by the bit addressable memory, and the last 80 bytes is occupied by the general purpose memory or scratch pad memory, and this whole is making up the 128 bytes of internal RAM of 8051 microcontroller. Now first let's discuss the register bank memory. So the first 32 bytes, that is memory from addresses 00H to 1FH, consist of 32 working registers. So how 32 working registers? These are organized as 4 banks with 8 registers in each bank. So as I've told you, this register bank area, it is further divided into 4 parts: bank 0, bank 1, bank 2, bank 3. Each bank is having 8 registers. So there are 8 registers in each bank. So if there are 8 registers in each bank and we have 4 registers in the registered bank area, so how many registers? All total 32 registers. 8 into 4 is equal to 32. 32 registers are there. 32 working registers are organized as 4 banks with 8 registers in each bank. Now, as you can see here, this is a register bank. This is one register bank. In this way, we have 4 register banks: bank 0, bank 1, bank 2, bank 3. There are 4 register banks. Each register bank is having 8 registers. Each register bank is having 8 registers designated as R0 to R7. So the 4 banks are named as bank 0, bank 1, bank 2 and bank 3. The 4 banks are named as bank 0, bank 1, bank 2 and bank 3, and each bank consists of 8 registers named as R0, R1, R2, R3, R4, R5, R6, R7. So every bank is having this 8 registers, and each register can be addressed in 2 ways, either by name or by address. So each and every register can be addressed in 2 ways, either by their name, that is like R0, or by the address. Now, to address the register by name, first the corresponding bank must be selected. Now, what is happening? There are 4 banks in the register bank area. There are 4 banks, but at a time only one bank can be active, can be made active. So at a time only one bank can be made active, and which bank can be made active or which bank to access at a time is decided by the bit addressing D3 and D4 bits of PSW. So I'll discuss about this in my next lecture. I'm ending this class here. Thank you.